hiya friends. You ready to go on an adventure with me in mechanics and materials? Well, if you are, let's see where our adventure is going to take us. Seems like in this video we're going to review how to calculate center of gravity and moments of inertia for cross sections. And then we're going to solve for the bending stress in members with singly symmetric cross section. And then, Dory, you're in the way. Silly Dory. If you stick around for another couple videos, you'll see that we're going to solve for the bending stress in members that are subjected to biaxial bending. If you're trying to remember what the bending stress formula is, Dory here is going to explain it again. Oh, it seems Dory's forgotten. Hopefully you remember though. If not, let's go take a little quick review of what that formula is. Alright, hopefully you remember what the bending stress formula is, but if you don't, the bending stress formula, remember, is sigma equals m times y over I, where m is the bending moment in the beam or member, y is the distance from the neutral axis, and I is the moment of inertia about that neutral axis. Now, if you have trouble remembering this formula, I like to just try to say it quickly, right? So we say my over I. So it's like my over I, my over I, my over I. And then you can shorten it to just be my over I, my I, my I, my I, my I, my I, my I. Hopefully that reminds you of the pelicans, the seagulls from Finding Nemo that shout mine. And hopefully that'll help you always remember the bending stress equation. My I, my I, my I. Now let's look at an example to apply this formula. In this example, we're asked to calculate the maximum tension and compression bending stresses occurring in a concrete double T member. Now, where might we see a concrete double T member? Well, we often use these members in parking garages, so I'm sure you probably have come across one in your life before. The parking garage shown here is at the Fox Chase Cancer Center outside of Philadelphia. And I actually took this picture when I was there with my dad about a year ago. And so I thought it would be a fun structure, reminding me of the concrete class and this double T problem. And I also want to give a shout out to those nurses at Fox Chase for taking care of my dad for all those years. Anyhow, in this member, we're going to look at it subjected to some sort of moment, and just think moment is the same as bending moment, and we can get this from the moment diagram for a particular beam. We can tell this parking garage structure is made up of double T beams because you can see the seam between each of the beams. So sketching out the double T cross section at the far end, you can see that this is what one double T unit looks like. And then it's supported on the right edge, or the far edge, as well as just above my head where I'm taking this photo. So I'll go ahead and sketch supports in. We'll assume it's simply supported, or that it has a pin on one side and a roller on the other. So this beam, with load from the concrete floor and all the parking above it, will be bending downwards, and we will, from what we learned about bending stress, we know that then along the bottom fiber of the beam we will get tension, and then we'll see our compression on the top portion of that beam. So I want to translate it from the picture back over to our problem. So in this kind of schematic of the problem, we can see the cross section. It's subjected to some sort of bending moment, and we're asked to calculate the maximum tension on the bottom
and the maximum compression occurring on the top. All right, somewhere between the tension and compression is what we term the neutral axis. And we say that the neutral axis, where is this located? Well, it always passes through the center of gravity for the cross-section. So it's not necessarily halfway along the distance or the height of the cross-section, but it has to do with the center of gravity. And we remember from statics, the center of gravity is kind of like where the cross-section is balanced about. So it's almost like a weighted average about that point. And then the weight times the distance above that point is the same as the weight times the distance below. Now, we want to apply the bending stress formula to find the maximum tension and the maximum compression. So I'll give these variables. And I'm just going to divide my page up to take a look at these calculations. So really all that we're learning when we're talking about bending stresses is we're learning the bending stress formula, which tells us that the maximum stress, or just any stress, is equal to my over I. We recall in last lesson that we defined m as the bending moment on the member. So in this case, it's given to us as 5,000 kilonewton meters. Again, we can always get this value for moment from our moment diagram for the beam or for the member. Next, we have y. Y was defined as the distance from the neutral axis. If we're interested in solving for the maximum tension, this distance will be from the neutral axis all the way to the bottom of the cross-section. So I call that y bottom. And lastly, we have I. I is the moment of inertia, and the moment of inertia will always be about the neutral axis of the cross-section. So all shapes, all members bend about their neutral axis. Unless they're somehow complicatedly constrained, they will bend about their neutral axis. And we can repeat these calculations for compression, and we'll see that they're basically the same, with the exception that since the max compression happens on the top, y is going to be the distance from the neutral axis to the top, y top. In order to calculate the bending stresses, we need to know the location of the neutral axis, which means we have to find the center of gravity for this cross-section. Now, typically, you probably would have learned center of gravity and moment of inertia in a course such as statics. And if you do remember how to do that, go ahead and make those calculations. But a lot of times when I get students in mechanics and materials, they forget. And so what do we do if we forget?
All right, well, if you're having trouble remembering the formulas for y bar and I, kind of like Dory, what do? Well, Dory has some advice. She says, you just keep calculating. Just keep calculating, just keep calculating, just keep calculating, just keep calculating. What do we do to solve y bar and I? Ha 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 ha, just calculate, calculate.
Well, let's get started on our calculations. So for this particular problem, we have a double T cross-section, and we know the neutral axis is somewhere in this location, and I've arbitrarily sketched the location of the neutral axis. I'm going to have to find the exact location here in a little bit, but for now, let's just put a line across the cross-section somewhere. Now we know that the neutral axis always passes through the center of gravity of the cross-section. And so we have to find the center of gravity. If we remember back to center of gravity, we know that the center of gravity is always located on an axis of symmetry for the cross-section. In this case, we have a singly symmetric cross-section, and that means that it's symmetrical about one axis. So if we can identify that axis of symmetry, we at least know the center of gravity has to be somewhere on that axis. So we see if we draw in the axis of symmetry vertically there, we know like the shape can be reflected about that. And we know that the center of gravity is somewhere in there. And I'm going to sketch it here at the intersection with the neutral axis. Again, I'm not really sure where the neutral axis is yet. Now the formula to solve for the center of gravity is equal to the integral over the area of y dA divided by the integral over the area of dA. And that's great if we're good at calculus. It's also great if we have a complicated cross-section. But when we have a cross-section like this that can easily be broken up into smaller shapes that we have good knowledge about, in this case rectangles, I like to approach it kind of as a summation rather than the integral. So I've located a point O, and I call that my origin, and everything's going to be in relationship to that origin. And so I've sketched my origin in some sort of XY axis. Now I'm identifying the different components or the different pieces, parts to this cross-section. So I highlighted in red there one particular shape. I'll call that shape 1. Now I'm highlighting in blue a second shape, shape 2. And finally, I'm boxing in and highlighting in magenta, shape 3. And I'll label these here in a second. Now you can use any kind of naming scheme. I like to use Roman numerals for my shapes, but that's just a personal preference. Alright, so I take a look at my formula and I see that the y to the center of gravity is the summation of y bar a divided by the summation of a. And so to facilitate my calculations, I could just go ahead and do my calculation all in one line. But I find a lot of times students like to have like a procedure to follow. And I think this table really helps us set out a procedure that we can just kind of solve. We don't have to think too much, and we'll get the right answer. So I'm going to look at shape 1, that's the red shape. And I want to get the distance to the center of gravity of the red shape relative to point O, or my origin. So on my figure, I'm going to sketch the center of gravity for the shape in red. Now we can pretty easily identify the center of gravity for a rectangle. Most everyone, hopefully listening, knows it's halfway up the height of the rectangle and halfway across the width of the rectangle. So that's the center of gravity. Relative to point O, it's 100 millimeters down, and you can see in my XY axis that is negative 100. Next, I need to take the area of the area in red. That area will be 2,500 millimeters, which is the width, times the height, which is 200 millimeters. And so this is going to give me something in millimeters squared, and it's a large number, 5,000 millimeters squared. 500,000, I think that's what I said. The last part to solving the center of gravity is just multiplying y bar times a. So I'm going to take column 2 times column 3, and I'm going to get an answer. In this case, it's going to give me negative 50 times 10 to the 6 millimeters cubed. Now I have to repeat this for shapes 2 and 3. So if you want to give this a try on your own, go ahead and pause the video and fill out the table. Fill out these columns for shape 2 and 3. Otherwise, you can follow along. The center of gravity for shape 2 is located where I just sketched it, 250 millimeters from the bottom of the cross-section. But relative to point O, it's 250 millimeters from the area in red, plus the thickness of the area in red, which is 200. So relative to point O, my center of gravity for the shape in blue is minus 450 millimeters. The area for the shape in blue is 150 millimeters times 500 millimeters. So that gives me 75,000 millimeters squared. And then I multiply the two together, and that gives me negative 33.75 times 10 to the 6th millimeters cubed. I have to do shape 3 as well. I take a look at shape 3. Shape 3 is very similar to shape 2. It's in the same relative position to point O, at least in the y direction. And so I'm pretty much going to get the same answers for the distance to the center of gravity, and for my area, and for y bar times a. So I'm just going to repeat those values in from shape 2. With this handled, we're ready to calculate y bar for the composite shape. Y bar is the summation of y bar a over the summation of a, so I'm going to add column 4, the results from column 4 together to get my summation of y bar times a. See, that gives me negative 117.5 times 10 to the 6th millimeters cubed. And then I'll add my results from column 3 for the area to get my total area of my shape. That total area is 650,000 millimeters squared. So I'll plug these answers into my formula. Take the summation of y bar times a and divide it by the summation of a. And put this in my calculator. I come out that y bar is going to be a negative 180.769 millimeters. Now I'm very careful here to label that this is y bar to the center of gravity from point O. Remember, I had to put my origin and I had to put my xy axis in place. And when I did that, I had to pick kind of a starting point to figure out what the distance to y bar. So my starting point was point O. Relative to point O, I move in the y direction a negative 180.769 millimeters. That will bring me to where the center of gravity is. And so I'll go ahead and sketch that distance on my figure. Returning to the previous page in our notes, we take a look at our cross section, and I'm going to go ahead and put the center of gravity there in this picture. We calculated that the distance to the center of gravity was 180.769 millimeters from the top. Or if I wanted to go to the bottom of the cross section, that would be a total of 700 millimeters minus that answer. Or 519.231 millimeters. All right, remember we said that for this beam, the bottom of the beam was going to be in tension and the top was going to be in compression. So if we're interested in sketching the stress profile, which we are, so I'll go ahead and label the tension and the compression on our stress profile. Now we know from the neutral axis down to the maximum tension point, that distance is 519.231 millimeters. So that corresponds to y bottom. And conversely, the distance to compression is 180.769 millimeters, or that's our distance y top. To finish that calculation, we need the moment of inertia about the neutral axis. So again, if you remember this from taking a class like statics, then go ahead and just calculate it however you're comfortable. The way I like to do is I like to think of the moment of inertia about the neutral axis is the contribution of the moment of inertia for shape 1, the contribution of the moment of inertia for shape 2, and the moment of inertia for shape 3. So sometimes I just do my calculations like that, and I'll look at the contribution of each segment or each area. Other times I like to take a look at it and I'll go ahead and put it into a table. Again, if you like a systematic process, having a table like this will help you quickly and easily calculate the moment of inertia for this composite shape. So I add 3 columns. The first column is ICG, and this is the moment of inertia about the center of gravity for each shape. So this is a particular property of that cross-section or that cross-sectional shape. For a rectangle, we learned that the moment of inertia about the center of gravity for a rectangle is 1/12 bh cubed, and that's probably a value that sounds familiar to you. So I'm going to go ahead and do this for shape 1. Shape 1, I'm going to put in my 1/12 bh cubed. Now, a lot of times we get confused on which to use for the base and which to use for the height. So since we're interested in the moment of inertia about the neutral axis, our base always has to be parallel to the axis of interest. So we're interested in the neutral axis, our base has to be parallel to the neutral axis, and then our height is perpendicular. So I've gone ahead and sketched in the base and the height on the figure above there. The base is going to be 2,500 millimeters and the height 200 millimeters. I go ahead and do some math. That's going to give me 1,666.67 times 10 to the 6th millimeters to the 4th. Now, we also know for a composite shape when we get these contributions, unless the shape, the center of gravity for the individual shape and the overall center of gravity align, then we have to, unless that happens, we also pick up an additional value from what we say the parallel axis theorem. And so that value is d squared a, and I have that in my final column. D squared a, it takes into account the parallel axis theorem for calculating moment of inertia. D in this case is the distance from the center of gravity of our composite shape to the individual shape's center of gravity. In my picture above, that's going to be just a very small distance. I've labeled it there D1, D for shape 1. And you can see it's going to be that distance from the center of gravity to the overall center of gravity. So I calculated the distance 180.769 from the top to my center of gravity for my composite shape. I'll subtract off 100 because that's half the thickness, or that's the distance to the red center of gravity. And that leaves me with 80.769 millimeters. After I do that, all I have to do is square that answer and multiply it by area, which I had in an earlier column, and I get the result for d squared a as 3,261.8 times 10 to the 6th millimeters to the 4th. Now I need to repeat these calculations for shapes 2 and 3. So for shape 2, the base, which is parallel to the neutral axis, will be 150 millimeters. The height, which is perpendicular to the neutral axis, is 500 millimeters. So 1/12 base times height cubed will give us 1,562.5 times 10 to the 6th millimeters to the 4th. Again, the center of gravity in blue does not match the neutral axis. So there's a distance between those two. So we pick up a d squared a term. That distance is going to be, if I go to the blue center of gravity all the way from the top, that's 200 plus 250. So that's 450 millimeters all the way down to the blue center of gravity from the top. Then I subtract off the y bar that we calculated, 180.769. And that now gives me the physical distance between where I have my black center of gravity there to that blue center of gravity. So that's a distance of 269.231 millimeters. Again, I just do d squared times a, and that will give us 5,436.4 times 10 to the 6th millimeters to the 4th. Finally, for shape 3 is just like shape 2, so we get identical answers. So I'll complete my table with those answers. Alright, so I'm ready to make my final calculation for I about the neutral axis. So I'm going to need all the contribution of the individual members plus all the d squared a terms from our parallel axis theorem. So I'm going to add up the summation of I about the center of gravity, and so I'm just adding this column together, and that will give us 4,791.7 times 10 to the 6 millimeters to the 4th. I also need to total this d squared a column. That gives us an answer of 14,134.6 millimeters to the times 10 to the 6th millimeters to the 4th. And so now I add those two answers together. I get to the final value, 18,926.3 times 10 to the 6th millimeters to the 4th. So don't forget your times 10 to the 6th millimeters to the 4th in there. There we go. Look, managed to correct that mistake. And so now we have I, the moment about the neutral axis for the shape. So we see that calculating the bending stress in this example was really just a lot about remembering how to do statics and coming up with the center of gravities and moments of inertia for cross sections. So this was more or less, nothing, terribly new. We're just now applying these previous values that we knew in exciting ways to calculate bending stress. So just bringing that value over for I from the second page back to our original calculations, we now have pretty much everything we need to solve for the bending stress in this beam. So I'm ready to solve for the maximum tension bending stress. Now, as with all calculations, we need to watch our units. And so I'm going to convert my moment into newtons and millimeters, since my y and my I are in millimeters. I want to make sure I get them into millimeters, and I'm going to convert to newtons. So to do that, I need to multiply by 1,000 newtons per kilonewton and 1,000 millimeters per meter. So that's going to give me now 5,000 times 10 to the 6th newtons times millimeters for my moment. So that's what I'll plug in for my moment. Plug in my value y, which was 519.231 millimeters. Then we divide by the moment of inertia, 18,926.3 times 10 to the 6th millimeters to the 4th. And so our maximum tensile bending stress is going to be 137.17 newtons per millimeter squared. We know that 1 Newton per millimeter squared is a megapascal, and so this will yield 137.17 megapascals. This is in tension. I'm just going to label it as such, and I'll indicate that with my parenthesis T. And there we go. We have one of our answers. We're down to the home stretch. Just gotta swim across the finish line. Let's repeat the same calculations for compression. So I make the same conversion for M. I have a different value for Y, and then I have the same value for the moment of inertia. So plugging those in, I get that our maximum bending stress and compression is going to be 47.76 megapascals. This is in compression, so I'm just going to indicate that with a C. Now, often, remember our sign convention that we're typically taking tension as positive and compression as negative. And so I add a negative sign just to indicate that it's in compression. But as long as you write that parenthesis C there, I know that you're telling me it's in compression. And so whether or not you have that negative sign, it's more important that you tell me if it's in compression or it's in tension. Now, some people like to keep a formal, track of their signs. And so sometimes you'll see that sigma equals negative my over I is the formula, where y is taking positive to the compression face. I find that a little bit confusing. I like to just remember my over I and then change my signs. I can tell if it's in compression or tension based on my moment diagrams. Finally, I'm going to put in my stress profile. And so we have a linear variation in stress, and it's 0 at the neutral axis. So you can see there I had to kind of move my line over to make sure that it's 0 at the neutral axis. And there we have our calculations from above. We have 137.17 megapascals in tension along the bottom of our cross section. And at the top, we have the negative 47.76 megapascals in compression. 0 at the neutral axis, which passes through the center of gravity. All right, well, I hope you're getting the hang of the bending stress equation. Sigma equals my over I. Again, we learned the bending stress equation. That was a new concept. But the values M, Y, and I are all things that we know how to calculate already from our previous classes and what we've reviewed in this class. So I hope you're excited to keep using this and find this formula useful in your engineering career.